Alright, hi everybody. So today I'm going to talk to you about a little bit more about fission and fusion, and then we're going to go into half-life. So I just want to wrap up the fission and fusion part of the chapter. To me, it's the most interesting part because it really has a huge application in our future and energy production and all these unfortunate nuclear threats and things that are associated with that as a negative. So this is really something that is important to us to understand. One thing that I wanted to talk to you a little bit about was the hydrogen bomb. This was the original hydrogen bomb that was used in World War II. And so understanding how it works is of somewhat importance. It starts off with a chemical type of explosive where there's a detonation. And that detonation will actually start a reaction that's a fission reaction. So this will be a fission reaction. And this fission reaction, it will actually generate enough heat to cause a fusion reaction. Sometimes they call this a thermonuclear device. And so that fusion reaction generates a tremendous amount of heat and energy. So this is the original hydrogen bomb that was used, and I just thought some people asked me about this, so I just thought I would present what it looks like. So let's talk a little bit about particle accelerators. This has been in the news a lot in the last 15, 20 years or so. The whole purpose of a particle accelerator is to try and understand the fundamental nature of matter and what are we made up of. The idea being that if you can collide particles together at a fast enough speed, that you will be able to basically smash that atom, generate all of these particles that are being made that are much, much smaller than the atom itself, being able to detect them. And this was really sort of the impetus for making something called CERN, which is this collider in Europe that is, a multinational, sort of project that was used to, develop and to discover matter that we didn't know existed. And so how do these particle accelerators work? Well, the idea is that you're able to use magnets in order to speed up or accelerate charged particles. And if you have particles from one direction and particles from another direction colliding at each other, when they hit each other, they will produce either new elements or they will produce new smaller particles that come out of this. So this is the most famous collider called CERN, and it's a Large Hadron Collider. And so you can see the huge size of it. This is the size of it here. It's in France and Switzerland. It spans 2 countries, and it's pretty crazy how large it is. This is the actual tube here where the accelerations occur. And there's a great movie that talks about the discovery of the Higgs boson particle, which is why matter exists, why matter has mass. They call it the God particle. And it's on Netflix. There's a great documentary about the making of CERN, the setbacks, the time it took, and then the discovery of the Higgs boson particle. And people were really worried about whether or not this existed because some people had devoted their whole lives to trying to, figure out, if the Higgs boson was real. Theoretically, it exists. They have this sort of model of all of matter, this unifying model. And if the Higgs boson did not exist experimentally, it would have forced them to sort of recreate and rethink their entire perspective on matter. We also have a particle accelerator that's much, much smaller here on Long Island at BNL, Brookhaven National Lab, and it's called RHIC, the Relativistic Heavy Ion Collider. And again, it's the same type of particle accelerator. It's doing the same type of thing where they are speeding up these particles and they are colliding them with one another and they're seeing what comes out of it. So let's talk a little bit about half-life for the rest of the video here, so that you can have a good idea of what half-life is. So when we look at the natural transmutation, just nuclides naturally changing into other nuclides, there's a certain characteristic amount of time that it takes for the decay to occur. And half-life is the time it takes for half of a radioactive sample to actually change into another type of element. And this will always be the same. You will never ever have it change. So when they ask you, does half-life change, the answer would be no. You can heat up the particles, you can combine them into compounds, you could decompose them back into elements, they'll still always have the same half-life. What variables will you be dealing with? Well, you're generally dealing with three variables. The amount of time, whether it's half-life time or total time, you're dealing with that. And then also you're dealing with amount. And in amount, you're also dealing with fraction. So these are the three main things that you're dealing with. Now, the way I look at this is I like to look at it in terms of an organized chart to show you. Let's say that you have 0 time. There's no time that has passed. And so 0 minutes, 0 years, 0 seconds, it doesn't really matter. Half-lives can range, you can look on table N, from seconds. They can range from a small amount of time to years, to billions of years. You can look at the bottom of the chart. Uranium-238 is about 4 billion years to undergo one half-life. So when you start at time 0, if you were to pick a random amount, like we could pick, 100 grams, your fraction that would remain would be 1 whole. If you were to then undergo one half-life, that would be a certain amount of time. We're going to say 1 half-life. Then you would have half left. You'd have 50 grams remaining, and 50 grams would have decayed. And your fraction remaining will be 1/2. If you go through 2 half-lives, then you'll be left with 25 grams and 1/4. If you go through 3 half-lives, you will go through, you'll have 1/8 remaining, and that's 12.5. And if you go through 4 half-lives, you'll have 6.25 and 1/16. I've actually seen them go up to 5 half-lives, where in this case you'll have 3.125 grams remaining, and you'll have 1/32 left. So when I do half-life calculations, the way I look at it is either through an equation or just by sort of mapping it out and going through each half-life and counting them on my hand, basically. I sometimes use arrows to do it. And I'll show you what this looks like on the side here. But before I do that, here's a graph of what half-life looks like. You can see that it's exponential. It's not a linear curve. And this is for SR90, which has a half-life of about 5.26 years. And so you can see right here at 5.26 years, they started with 10 grams. They have, oh no, that's the amount. My apologies. It's about 30 years, 29 years. So it has a half-life of about 29 years. We started with 10 grams. It has half the amount left, 5 grams. When it undergoes 2 half-lives, so now the amount left will be half of 5, so about 2.5 grams left. But notice the time, it's added on another entire half-life. So instead of it being around 29, now it's close to about 58. If we do 3 half-lives, we cut the amount in half again. We'd be down to about 1.25 here. And then the time would add on another 30 years, so then we'd be close to 90 years. So the half-life amount of time stays the same, but the amount of material gets cut in half. And one way of looking at this, a good equation to use is number of half-lives equals the total time over the time of one half-life. And so this will allow me to say how much time has passed. And as far as the amounts are concerned, what I like to do with the amounts is once I know the number of half-lives, I can use those number of half-lives and I can find the amount. So let's say that I went through 3 half-lives. If I went through 3 half-lives and I started at 10 grams, I would go through 1 half-life, that would give me 5 grams. That would be 2 half-lives, 2.5 grams, and then 3 half-lives, 1.25 grams. So when I do amount, I like to do sort of a graphical approach, and I like to go through it how many half-lives using arrows. In this case, I went through 3 half-lives, 1, 2, 3. For the amount of half-lives, to figure that out, or the time, I like to use the equation approach. Now let's just try one problem here, and then you could try some on your own, and we can also go through these in class as well. But let's say that we have 80 grams of P32. How many grams will remain after 57.12 days? So first I need to find the half-life, because I have the total time. The total time is 57.12 days. If I find the half-life time, and I can divide it out, and I look at the half-life time, I think it's 14.3 days. 14.3 days it is. So if I divide this by 14.3, I will actually get the number of half-lives. So let's go ahead and do that. 57.12 divided by 14.3. And when I do that, I get 3.99. So I'll round it to 4 half-lives. Well, how much would remain after 80 days? So let's see here. It's 80 grams. So we have 80 grams. Then we go to 40. That's 1 half-life. 20, 2 half-lives. 10, 3 half-lives. And 5, 4 half-lives. So I'll have 5 grams remaining. Let's say I were to try another sample here, another problem where we have 2 grams of a sample remaining after 8 years. The half-life is 4 years. How much was originally present? So let's see how many half-lives we've gone through. So we have the total time, 8 years. 8 years. Over the half-life time. The half-life time was 4 years. That means that I went through two half-lives. That means that I went through 2, if I do 2 arrows, 2 half-lives. Well, now I have 2 grams remaining. So 1 half-life prior to that, I would have had double. I would have had 4 grams. And originally, I would have had double that. I would have had 8 grams. So you can see that if I know the number of half-lives, which is really the most important factor here, the number of half-lives, if I know the number of half-lives, I can find out how many arrows to draw and how much is remaining. Let's take an element like here. I'll do this last problem with you and then with this one. So they tell you that Na24 decays from 250 to 31.25. So 250, that's the amount. So let's go and cut it in half. 125, 62.5, and then 31.25. So look at what I found here. I found 1 half-life, 2 half-lives, 3 half-lives. Now I can use my equation. Number of half-lives, 3, equals the total time, 7 days, over the half-life time, x. Well, 3x equals 7. So x is equal to a little bit above 2. 7 divided by 3 is 2.33 days. So what I want you to do is try one on your own. Here's a half-life problem down here. What fraction of carbon-14 remains after 22,920 years? Don't forget where you can look up the half-life in Table N. So look, that's it for this. We're going to do one more quick video in which I'll practice a few more half-life problems with you again in case I see in class you're a little bit shaky on it. We'll do some more. And then I just want to talk to you about uses of radioactivity and some cool things with that on my last video for this chapter. All right, thanks so much for watching, and see you next time.